the well, it's obviously a great honor for me to give this talk, and I realize I have in my audience some of the deepest and the brightest minds in New York City and surroundings. However, I was asked to give a very general talk, and so this was aimed to be a very introductory talk about probability. And the first person I meet, of course, is Chuck Newton. And I do apologize. It's going to be extremely basic, and it won't be about my work. It will be about very old ideas, and which I'm sure you've heard and understand very well. And anyway, so with this said, let's go down my experiences, and before we start with the subject proper of the talk, I want to say a few words about how difficult it is to communicate our current research, not just to fellow scientists, but in fact to colleagues in other areas of mathematics. Math is growing at a wonderful and very exciting pace, but that means it's also growing. It's like a universe expanding. It means all the galaxies run further and further away from us, and so it becomes harder and harder to communicate what you do, not just to other scientists, but in fact to other not even to other mathematicians, but in fact to other people in essentially the same general area of math. And that's a fact of life, and it's also a fact of life that math is driven not so much by, I mean, of course, math is driven by application, but actual progress, where it happens, is not so much because there is a problem and we need to solve it, but more because we discover certain deep structures and we just follow those connections. We discover something that works, and we experiment more and more with it, and in order to find something we find interesting and amazing. And it's math is certainly not alone in this situation, because while I'm not a chemist or material scientist, but I imagine that the logic in those fields would be also to, if you found a really cool material, you just experiment with it and then look for applications later. And you don't set out to solve the world's fuel problem or the world's food problem. And the same goes with math. There's certain eternal problems that's been standing there forever, and we in absence of good ideas, we just follow our ideas and not trying to solve the eternal problem. So this unfortunately means we go away from what other people do in daily life, and we go away from things would be easy to communicate to our colleagues. So therefore I felt that it'd be maybe in the general science audience, a reasonably okay topic would be to talk about something extremely basic, something we're all familiar with, so we don't have to somehow I'm hoping we could immediately relate to law of large numbers. That's been with us for centuries, and it's really not it's really the beginning of probability theory. It precedes even the central limit theory, which most people would associate with as really being the first meaningful result in probability theory. And so, what is the law of large numbers? And in English, it can be said, well, you can say it in many different ways, but maybe one way to say it is if you have something random and large, then on that large scale, it won't be random. So you won't see the actual randomness. So a typical example that's going to come later in the talk is if you look at say, crystalline surfaces. And the surfaces are composed out of individual atoms. And if we examine the surface with a microscope, or if we run a simulation, well, this is a simulation, that's an actual picture on the other side, then we see that it is on the microscopic scale, it is random. However, on the macroscopic scale, it is not random. It is something which things around us, even though they're random, they don't appear on the random they're random on some microscopic scale, but not on the scale of our daily life. And the same if you're say a more socially minded person would give an example with say economic behaviors, the forces of laws of economics. They somehow they manifest themselves through myriads of individual random events, and then on the scale of the whole economy, something non-random happens. And that's I hope this somehow this is look extremely familiar, and even so we will take so to really make sure we're all on the very same page, let's talk about a simple random walk, which is it's equivalent of tossing coins, and it's one of the first things you ever learn about probability, and this is what we do every day, or some of us at least, is that if we have to get from point A to point B in Manhattan, then we go either along the street or the avenue, whatever the light might be, or whatever the fewer cars could be, and so we can you can of all possible paths on the from point A, say from this time from the fair to somewhere around Roosevelt University, you can take all these possible zigzag paths and take them equally likely, and this would be a random walk from through Manhattan, midtown Manhattan, from east side to west side. And maybe more geometrically, a random walk, if you draw it like this, we could take 2 points on the plane and consider just a random zigzag curve that joins them. And I said we will take them all equally likely. So the difference between the previous picture and this picture is that of course here the city blocks have different sizes, but here I scaled them, so I changed the coordinates so that all the city blocks have the same size. And so if I now the real probability begins when you let the system be large, or the number of steps of the random walk be large, or equivalently, we can take the mesh of this picture to be small. And if we do this, then if we take a random walk with very small mesh going to 0, then what's going to happen is the randomness will disappear in this picture, and we will see a straight line. Now, most of you are much more advanced level, and you know that about the convergence of the random walk to Brownian motion. Now, for this conversion to happen, you have to scale the time, you have to scale the axes differently. If you scale them like I scaled them, you're just going to see a straight line. And why is this a straight line? It's because straight line solves a certain optimization problem. So this is the title of my talk, the most random of the all possible worlds, refers to the fact that things we actually observe, the non-random things we observe on macroscopic scale, they happen because they solve a certain variational problem. And the variational problem is they just maximize the probability to occur. So in other words, this straight line has many wonderful characterizations. And for example, it's the Euclidean distance minimizer. This is not why it appears here. And there are not so many. Straight line is a solution to many different optimization problems. And the ones we're going to discuss in a second is the one which just look for the macroscopic shape that observes the maximal amount of probability that's happening. It maximizes its probability to happen. And the way you set it up is you suppose you have some curve. Well, it's in this case I've drawn a parabola, but it could be any curve. And you want to know roughly what's the probability that if I draw a trajectory of random walk, a random zigzag path, what would be the probability that this zigzag path stays close to a given curve? In other words, I have to count. What I have to do is I have to count all possible random walks that start from. There was a pointer somewhere. And, let's see it now. But maybe I'll just be pointing with my finger, or maybe I'll point with the mouse. You count all possible curves that start here and there and stay close to a given curve. And the way to count it is you can break up the curve in relatively small pieces. So pieces which are small compared with the whole curve, but large compared to the mesh size of my random walk. And then since what a walk does on one, so here I've broken it in 6 pieces. So since what the walk does, thank you so much. Red. Oh, it's not visible on the screen.
I think you want to turn it to point the red thing at it.
Well, yeah, I'm doing this. You see, it's visible on the ceiling.
Because you're pointing it up. You have to.
180 degrees.
No, it's not going to work. It's just use your mouse. Yeah, it's
Not showing up.
So what this curve does on one of these segments is independent in this case, literally independent of what it does on the other. Therefore, the number of paths that follow that stay close will just factor over this pieces of the subdivision. That is to say, if the numbers factor, that means the log of the probability, if we're interested in the probability, it's logarithm. If probability factors, then this logarithm becomes additive. So the log of the probability will be an additive function of the curve to which I'm trying to stay close. And therefore it has to be, and there it has to be it has to be some function of the slope. There's nothing else it can depend on. Some function of the slope of the curve, just integral of that function and 1 over the mesh size. It's just the only additive function there is. And this function s is at this moment is unspecified. Well, of course, it's not a big secret what it is, but all I'm saying is that that's a general formula we're going to discuss over and over. That if I'm interested in the probability of a random curve of a random surface staying close to a given non-random one, then this would be the log of this probability is given by 1 over the mesh size here, and if it's a surface, it's going to be squared and cubed if it's a random three-dimensional thing. And then some integral of some function of in principle could be if I were walking in some anisotropic universe, in principle there could be x and f here. But since I've already since all my the properties of my walk here and here are the same, and they also don't change with vertical axis, it's just a function of the slope. Yeah. And so this function s, it's known many different ways and many in areas probability theory in mathematical physics, it's somehow people in random surfaces, people like to call it surface tension, or more generic probabilistic name for it would be entropy, and a mathematical physicist would say this is effective action. And what it does is, as I said, it counts the zigzag curves of a given curve, of a given slope. And for a simple random walk, or maybe for a simple random walk, it's very easy to count random walks of a given slope, just because you have, if you know the slope, you know how many times you have to go up and how many times you have to go down. And all your freedom is just to choose at which moments of time to go up and at which moments of time to go down. So this count for a given slope is just a binomial coefficient. And this function s is just log of some binomial coefficient. And with the log of binomial coefficient, it has a very simple asymptotics code known as Shannon Entropy. It's this function, p log p, 1 minus p times log of 1 minus p, where p is the frequency of up steps you have to take. In other words, as your walk follows this path, and depending on the slope, you have to take up steps with a certain frequency. This frequency, let's denote this frequency, p. And then this function s is just this Shannon entropy of the p log p. And as I said, for many more general instances of random curves, random surfaces, and so on, the probability to observe a certain macroscopic shape, the log of that will be well, traditional people put minus here because people like to minimize as opposed to maximize. If you maximize something, you appear greedy. If you minimize, you appear cool. And then the integral over that surface of a function that tells you how many microscopic configuration that the surface absorbs, this macroscopic configuration absorbs. And this could be in principle a function of not just the first derivative, it could be, but it could depend on the function itself, could depend on x, and most importantly, the prefactor will be just meshed to the size of the dimension. And the conclusion of that from this is that if we let this mesh go to 0, then the probability to observe any particular configuration will be extremely strongly dominated by one given configuration. That's just because this functional s, functional means a function of a function. So that is to say, a function that sends f to this integral. This functional is typically a convex functional. It has one particular extremum, and then whatever is not, and that extremum incidentally has to be 0 because it's log of probability. But wherever this thing is positive, then this probability is suppressed extremely strongly because you see it's a log, so it's going to be exponential of 1 over some very small number to a power. And we also see that this basic argument shows that curved surfaces and maybe membranes of higher dimension fluctuate differently. The bigger dimension, the sharper is the law of large numbers, because this suppression is going to go stronger and stronger. And now the straight line we see is because if dimension is 1, so this is just a function, f is a function of one variable, and if it only depends on the derivative, then whatever convex function s we take, the straight line will be, just by convexity, will be the maximizer. So it's it wasn't essential that for the random walk here, the Shannon entropy was something. We take any convex function, And then just just because it's convex, this solution will always be straight line. Dimension 1. And similarly, if S is only a function of a slope, and S is convex, then a plane, say in 2 dimensions, a plane is a solution if it satisfies the boundary condition. And it's not the point about dimension 1 is that for any boundary condition in dimension 1, you can always fit it with a line. But with 2 dimensions, most boundary conditions are not planar, and so you cannot fit them by a plane. So you're going to be something more interesting. And one thing I want to point out, and that's which I didn't plan to discuss today, but if in this formula you can, once you found the maximizer, you can expand around it, and this will at least be at least a good prediction for what to expect in terms of the Gaussian flux. So the law of large numbers says that things are non-random. The macroscopic behavior is non-random. You have something deterministic. But then around it, there's some fluctuation that's typically Gaussian. And what these Gaussian things are, again, typically, they're found just, you can, at least heuristically, you can find what they are by just expanding this function around that extreme. This will have some Gaussian expansion, most functions do. And of course, for a random walk, this will be the Brownian motion. Now, well, I hope what I said so far is just completely non-controversial. So there's well, of course, it's fun to discuss it, but it's all extremely classic. But now what I'd like to discuss is the situation where something very similar happens, mathematically speaking, extremely similar. But the consequences that one can draw from it are rather surprising. Certainly, I found them surprising when I first saw them. And I hope you will too. So it's again about a random walk, but now the walk will be on a slightly different nature. Mathematically, it will be a walk on a finite group, on a large finite group. Now, to review what we had before, previously we had this walk on well, in Manhattan we go on the 2-dimensional lattice given by 2 coordinates, the avenue number and the street number. And the basic movements correspond to either changing the street number by 1 or the avenue number by 1. And then yeah, you should point out that then this is really should go on this side, right? Somehow a generalization of this is you can have the states of your random walk to be drawn from some arbitrary set on which some generators of some group act. For example, it could be group itself. So group, if you're not familiar with this notion, it's not important. You can think of just permutation. So the set will be just permutation of n objects. There's n factorial of them. And the elementary transitions correspond to some given set of generators of a group acting on this set, and this is the group itself. And what I've taken in this case, well, what you can do with a permutation, you can transpose, you can switch to neighbors, you can transpose to neighbors. And so suppose you have a permutation of an object, in this case 4, and at any given moment you can flip a 3-fold coin and transpose either this two neighbors or this two neighbors or that two. Does that make sense? So previously the group, if you want to think of group theoretic terms, previously the group was the lattice set 2 and we choose particular generators. And here I choose particular generators of the permutation group. And you can view this walk geometrically if you just take a vector. Permutation of an object is a vector in M space, and these vectors they lie on a certain n-2 dimensional sphere. Well, because the sum is fixed and the sum of squares is fixed, and on that sphere, if you the two nearest, if you just draw the points on that sphere, every point will have a permutation of an object. Every point will have n-1 neighbors, just nearest neighbors among the points, and which will differ by you permute. Well, I don't know if you can read it, but two neighbors correspond to the fact that the Euclidean distance always wrote 2, and it corresponds to the fact that you take two numbers that are differ by 1 and you permute them. Here it was 2 and 3 and we got 3 and 2. And permuting two numbers that differ by 1 and permuting two neighbors, these things are equivalent of if you replace permutation by the inverse permutation. So anyway, somehow mathematical is just the same. And so it's really just nearest. So you have a collection of points, of n factorial points on n-2 dimensional sphere, and at every tick of time you just jump to one of its nearest neighbors randomly. It's just a random walk on this graph. Just like this graph replaces the lattice of the streets and
So some transpositions are not allowed.
What?
Like if you permute 1 and 3 on that vertex, you would then.
In this language, this is about inverse permutation. Means you always permute numbers that only differ by 1.
This is a representation where you do only one change of numbers that differ by 1, and the previous one you did 2 of nearest neighbors. Is that correct? And those are equivalent. That's what you're
exactly. So if you replace a permutation by inverse permutation, what's going to happen is when you replace the two nearest neighbors is the same as replacing two numbers that differ by 1. More questions about it? So extremely. And this random walk has been studied in a recent by the scale of my previous examples were drawn from hundreds of years ago. That's by that scale, it's a very recent paper for a very promising young probabilist, and they studied a particular instance of this random walk. They were studying a random path that connects two antipodal points. In the sphere, the points 1, 2, 3 in increasing order, and the points the same numbers in decreasing order form two antipodal points. And you can ask for it's like in this Manhattan picture where we're looking for all possible. Here, where we're looking for all possible, what's it called? The northeast paths from here to there. And similarly, on this sphere, you can ask for all points from one point and antipodal point. And the analog of the northeast condition is that this path has is a minimal number of steps you can reach from one point to antipodal. There's no looping on.
So as you increase in the areas of these plaquettes, they are roughly the same. The faces of your polyhedron, they don't have a lot of variation, the areas of those spaces?
Well, the faces of any given dimension, they stay more or less the same. But what's crucial about it, that what's crucial in the analysis, that this permutation point is extremely sparse. If you increase the dimension, then they become sparser and sparser in some sense in the set of all in the sphere. So they're not particularly dense in it. And so we will get that in a second. So in other words, you consider right. I mean, there's actually a lot of ways to so in other words, a path on this sphere is a way to, you have in this case 6 elements, and you want to put them in opposite order by switching 2 neighbors at a time. It's an example of what's happening. And there's a huge number of ways to do it. The reason they studied this is that it's combinatorial. The set of this path from one point to the opposite extremely well understood. They could sample from it. They could somehow bring all sorts of combinatorial machinery to analyze it. And it's one of those things in mathematics where somehow certain problems are better than others just because there's so much extra structure that they possess that if they were studying just a slightly more general problem, that they wouldn't be able to do it. So this is the reason they focused on this one. And so what's their, unfortunately, their main conjecture is a conjecture. And I've given talks about it. Maybe I'll come back. I've given talks about this before, and I kept trying to interest more young people in this problem, but still remains a conjecture. I still think it's the machinery to solve it is there. It's just just because of the richness of the problem, I'm quite sure this particular one can be done. Anyway, the main conjecture is that if this path from one point to the antipodal point is in fact stays close to a great circle, which is analog for the sphere, is the analog of a straight line. And then maybe you can try to generalize this conjecture by saying, well, if I walk from any point on the permutation to any other point, I'm going to stay close to a great circle. That conjecture has to be false, just because the crux of the matter is that this permutation are so sparse in this sphere, and so if you just give you 2 random permutations, in fact the great circle from one to another may not be approximated well enough by path of permutation. There's just no way. And in fact, it's not what we'll see in a second, the great circles that actually connect these 2 antipodal points through permutations are extremely constrained. And this is what's so surprising. So maybe a better statement or a better potential generalization of their conjecture is that if the 2 permutations are such that the great circle that connects them can be approximated by permutation, then the walk follows that great circle. Otherwise, who knows?
Can you explain? Up there, it's only antipodal points, and down there, the question is whether it generalizes to other. What does whenever possible mean? When the points aren't antipodal?
Right. So if you give me 2 permutations, or in fact 1, say 1 could be always assumed to be identity, and then some other. Give me 1 permutation, and I draw. So this, if it's not antipodal, it will be in fact unique great circle connects them. And if I draw that great circle, this typically will not be approximated by permutation, with no path and permutation that stays close to them. And so, and so then the generalization of the conjecture would be if it is possible at all for permutation to stay close to a great circle, then they will stay close. Otherwise, somehow, you know. This otherwise it looks like a hardware problem. But in particular, for antipodal points, there is a whole bunch of great circles that can be approximated by permutation, and the conjecture is this particular walk stays close to a great circle.
Can you give a simple example where it is clear you kind of can't do a great circle?
Oh, very easy. So you can take, let's see, so you, I don't remember offhand, but it's something like if you take like block permutation, if you take two. If I have to look in the paper, but if it's I think something like if I take just a block permutation that reverses the first n over 2 points and then reverses the other n over 2 points, it's impossible. Something like that. I forgot. Yeah.
There's another thing which I think I was slightly confused about.
Mm-hmm.
When you talk about an n-2 sphere, you mean a 3-sphere approximated by n permutations of n objects.
No, the permutations sit. Well, the permutations sit naturally in n-2 dimensional sphere, n-2 dimensional sphere. Because they sit in n space, but their sum is fixed, so they sit in fact in n-1 dimensional space. And their sum of square is fixed, therefore they sit in n-2 dimensional sphere. They also, of course, the sum of cubes is also fixed, so this sum of fourth power is also fixed. This is why they're so sparse. More questions? And so this is, as I said, this if given our previous discussion, this would seem like a very easy conclusion to make, but in fact it's quite surprising. And so let's look at this. So in particular, it says that in this diagram up there, it's just we saw this before. It's a diagram in which the numbers 1 through 6 got put in the opposite order by permuting to the time. We can try to follow a path of one particular number. And what this great circle conjecture says that any particular number will just follow the graph of sine function. The amplitude and the in the phase of that are random, and there's a certain distribution of this. But otherwise, it's a non-random curve. It's a sine function. This is simulation, I believe, for maybe several hundred.
So you write out 1 through n, and you track a number, and I'm going to get a sine wave.
Exactly.
Cool.
In particular, it's not at all that the numbers you're thinking of. The numbers are just going to somehow try to go straight where they have to go. But in fact, they all follow a sine to get where they want to go.
As n gets large.
Yes.
Sine.
Yeah. So.
There it's a bad approximation.
Well, 6. I don't know. I think. Well, it's debatable. I think it's not so bad actually.
Well,
yes. But this, of course, this is very. This is just taken from their paper.
An actual simulation.
An actual simulation, yeah. This is why, as I said, the reason studied this is just because they could sample from them extremely effectively. Otherwise, if you, but they had this path they considered they're in bijection with some other set, combinatorial well understood, and therefore they could really effectively sample from this.
How large does n have to get before you roughly get this?
I don't know. I mean, I think it depends on your definition of roughly. I think like you think the speed and converges to this.
Yeah, I mean, is there something like 1 over square root 10 or the width of this compared to the whole?
I don't know. I mean, I'm not sure. No.
600 dots per inch, 8 inches, 4,800 samples there, probably?
No, that's just one sample. I mean, yeah, but the point is that it could just perfectly sample it. And sometimes sometimes in probability there's magic situation when you can just perfectly sample from the distribution. So this is what this is what happens here. Also, you can ask for so if you have a permutation, is after all a map from you have n object and you put them in different objects in different order. So it means you have a map from endpoint set to endpoint set. Right? Every object goes to some other place. And you can consider that map has a graph, which sits on so a graph of this map would be a bunch of dots which range on there's a well this in 2000, so there'll be numbers going from 1 to 2000 here to 2000 there, and then it's a graph where each of this permutation analogy and object goes somewhere and it's a point in the graph. And so again, this great circle conjecture says that this graph, if you draw it like this, it's a bunch of points. This density of this point is non-random. It's in fact always it's always supported on an ellipse. An ellipse. So you start with that density permutation, it's on the diagonal, then it gets a wider ellipse. At exactly midpoint, it's a perfect circle, and then it gets squared the other way until you go to the permutation and put them all in the opposite order. And not only it's a perfect circle, it's in fact the density of dots is just if you take now a three-dimensional, so it's a two-dimensional sphere, just ordinary two-dimensional sphere like we've been drawing all along, and you project on the plane, then the image of the surface area, which you can of course write down in trigonometric functions, this will be this density. That's and there's more. There's I hope you agree that's extremely cool. This analysis and due to the various due to extremely elaborate algebraic machinery to which this is equivalent, I'm quite certain it's going to be proven soon. But I've been it's anyway. So in the rest of the talk, I wanted to talk about certain two-dimensional analog of random walks, and that's going to be about certain random surfaces. And these particular ones are called, people call them stepped surfaces. And what is a stepped surface? A stepped surface. So a random walk had an up step and down step. So it was composed out of two elementary steps. It could go up or down. And now it's going to be a surface that will be composed out of three elementary pieces, which are just the sides of the unit cube. It's like if you take a unit square, its sides constitute the up step and down step, and you can draw your random walk out of that. And then the now surface is going to be glued on the side of the unit cube. And in the condition that we have the zigzag curve, it translates into the condition that the surface has no overhang. It just really is a two-dimensional analog of random. It's the most natural one. And just like maybe I'll go back here. Here we took all of any curve composed out of this up step and down step was given an endpoint and took them equally likely. And so now in 7 2 dimensions, we can get any surface composed out of these three sides of a unit cube, no overhangs. But now, instead of curve going from here to there, it will be a surface spanning given boundary, otherwise equal. And one reason, I mean, of course, this is this is such a simple-minded model that probably needs no justification why people consider it. But in case more justification is needed, that this is really if one of the preferred ways to analyze interfaces in mathematics is the Ising model. In 3 dimensions, it's extremely challenging, but at 0 temperature, it's this. So, and so this could be viewed as of course extremely simply-minded, but qualitatively okay, I think, model to illustrate the various features you see in crystalline interfaces. And if you're interested in the law of large numbers, that's been established in the work of Henry Conrich and Kane and Jim Propp in this form, as the form we discussed, with a particular function f. I'm not going to write a formula. It's some explicitly known function f. And so, in particular, if for any given boundary, if you want to know what's a typical, if I take a typical surface, typical small mesh surface spanning given boundary, I can find it by finding an optimizer in a certain explicit variational problem. But this variational problem has some good features and some not so good features. Well, first of all, this variational problem is going to be, of course, harder than what we saw in one dimension, just because there's much more solutions to that. That's a PDE. PDE has many more solutions. Or if you not ODE, or put it differently, if you're interested in some variational problem for surfaces, there's so many more boundary conditions you can consider. So there's going to be certainly many more solutions to your problem. But that's a general somehow general complaint, right? This applies to minimal surfaces too. The specific feature, the specific bad feature of function f is well, first of all, it's very nonlinear, and it's this means if you write it as a PDE, you're going to get terms like cotangent of the first derivative, so which is genuinely speaking people don't like. And most importantly, in fact, it's singular, and that's the feature for which we'll like it, because the singularity of this function surface S as a surface tension or entropy or whatever you call it, effective action, in the singularities of this function is what's responsible for formation of facets, and it's in this somehow event in this model crystals or actual crystals, and it's this singularity that makes it a model worth studying. And as I said, the straightforward PDE approach to that is probably it's quite difficult. But on the other hand, this simple simulations, which we can always do, they show a certain structure to these limit shapes or the optimizers of the surface tension. And before we start with general theorems, let's just look at the simulation. And this we take. I took this out. So this is supposed to be a surface, and my step surfaces was glued out of size of unit cube. It's a surface in 3 space, and I'd like it to span given boundary and let it span this boundary. Which is I took a cube and I made a little dent there. And we can certainly, before we do any general theory, what we can always do is just sample from this. It's like in the the very good old days of minimal surfaces, people were literally putting wires in the soap and then examining what's going to happen. So so that's exactly analog of this, and maybe computer analog. So so that's a simulation, and I apologize if you've seen this picture before. And the maybe the most interesting feature of this simulation is that all along the boundary there is no disorder. It's just completely ordered all along the boundary. And that's ordered means it's ordered to within one box. It's not just approximately flat, it's just really flat. And that's this is exact same feature as the reason that it's so finely ordered all along the boundary is ultimately the singularity in the surface tension, which is also the same thing, that exact same mechanism that drives the formation of the cradle facets in natural crystals, which are also incidentally ordered to down to the microscopic scale. And this region, well, this is a small simulation. We're going to look at a larger simulation in a second. This region are separated from the region where actual disorder occur by a certain curve. And this curve turns out to be a curve, one of these curves that already have a name. It's called cardioid. And just because it's heart-shaped, not because John Cardi invented it. So it's just the shape of this curve. And if I look at the larger simulation, I think it's kind of obvious that this is this formation of this cardioid is there. And one actual question I've always asked whenever I talk about it, I always ask the people with any sort of access to actual materials, is if ever at all, one could actually in a laboratory crystal see a point like this. So it's certainly here this might be, so this point in the previous slide, you see there's this cardioid has a cusp. There's a singularity there, and it's mathematically it's extremely interesting point, because if you're interested in behavior, what this random surface does, well, it has a certain relatively well understood behavior in the bulk of the disorder. It has also relatively well understood behavior right at the boundary. This has to do with all this KPZ scaling and so on and so forth. This is also something very interesting happening here. It has to do with finite size random matrices. But there, the cusp is a different behavior. It's also mathematically studied, but it's not. It's like in this KPZ scaling things. It's like the next case, and this is it'd be I think. You know, people this sort of randomness, people experimentally with like propagating flames and so on and so forth. People do good get results, get good results here, but it'd be if any actual somehow laboratory thing would ever get you a point like the cusp there in the cardioid, I think that would be interesting. So anyway, going here, so larger simulation here, and the general statement would be well, maybe let's talk about this picture first. This is one way to mathematically define a cardioid. If you take a circle and let another circle roll around it, and you follow a point of that circle that rolls around the one bigger, then it traces how this curve is called the cardioid. And what's obvious about this, that since a circle is defined by a equation x squared plus y squared equals the radius square, and another circle is also defined by quadratic equation, the resulting trajectory of this red point would be defined by equation of over degree 4. The substitution of quadratic into quadratic. And this makes a cardioid an algebraic curve, the zero set of a polynomial in two variables. And we already discussed that its degree is 4. Now, what makes cardioid different from most curves of degree 4? If you write down a general equation of degree 4, you would not be able to parameterize the set of solution by functions of one variable, or say by rational functions of one variable. Whereas for cardioid, you can. It's obvious in this parameterization you can parameterize it by trigonometric functions. But whatever you can parameterize by, so if you parameterize two coordinates by trigonometric function of one variable, whatever you can parameterize by trigonometric function of a variable, you can certainly parameterize by a rational function of one variable, just by a tangent of a half angle, or any other way to parameterize the circle you like. And so, the takeaway from this transparency, there are two notions. One is that of an algebraic curve, the zero set of polynomial in two variables, and another is a special property of an algebraic curve. Sometimes it's rational, means can be parameterized by two functions two rational functions of one variable. And this will not be the case for general degree force curve. And so with Richard Kenyon, we proved a general theorem that implies in particular the following statement, that if I suppose my boundary is such that it's formed by 3D dv some parameter, and I take 3D segments going in coordinate directions and cyclically repeating. So this is I took 5 segments of each orientation and I use them in cyclic order to form this contour here. Then the facets will be bounded by an algebraic curve that's uniquely characterized by the following fact, that it has degree d. Sorry, it doesn't have degree d. Its tangent vector rotates d times as I go around, and it's rational, and it's inscribed. So there's a unique rational curve that does this. It's roughly how it looks like. It makes one cusp for every indentation like this. And so the first statement is that the deformation of the cardioid is just completely general. This would be this what we call this frozen boundary, or the line that separates the facets from the disordered region will always be an algebraic curve, and in fact unique one, which is rational and whose tangent vector rotates d times. And in fact, this curve determines the entire shape in the following way. So, so here, let's look at this. Here d is 3, and this the curve in question is the cardioid. And as we discussed, its tangent vector, as I go around the cardioid, the tangent vector rotates 3 times. Means if I fix any point outside, so if I fix a point here, there will be exactly 3 tangents to the cardioid through this point, because if I follow the line that rotates 3 times, it's going to hit this point 3 times. Now, however, let's take a point in the interior. Then it's very easy to see here an example, and you can convince yourself in general that in the interior of the curve, you'll have 2 fewer tangents. Like here, if I'm in the exterior, through a point in the exterior of a curve, I have 3 tangents to my cardioid. and for a point through the interior, I only get 1. What does it mean? It means that if I write to have a tangent, through a given point, to a given curve, is if the curve is algebraic, then this is an algebraic equation. And this equation, therefore, has a different number of real solutions inside, depends on the parameter, on the position of the point, and it has 3 real solutions outside of the curve, and 1 real solution inside of the curve. That means it has, if you have an algebraic equation, 3 solutions in one region and 1 in the other, means exactly 2 gone complex conjugate. Does that make sense? Means that in this, if you take look at this real picture, that through every point inside, there is unique up to complex conjugation, complex tangent. So it's a real point inside a real curve, but the tangent line is complex. And you don't have to think about cardioid, think about a circle. You think about a circle, outside the circle you have 2 real tangents, inside the circle you have none. Means they both gone complex. So this means you take this, whatever it is, it's the complex line. Complex line means it's an equation ax plus by equals some constant, but now with complex coefficient a and b. Okay? Means, and then of course this line is uniquely defined up to complex conjugation, means its coefficients are uniquely defined up to complex conjugation and proportionality. Because if you have an equation of a line is only defined up to a constant. So it means this a and b are uniquely defined up to overall scaling, multiplying by a and b by the same number, and complex conjugation. So that means that if I record this ratio, I call it z, which is a over a plus b, this is, first of all, this is independent of the scale. So it's only defined up to complex conjugation. But if I make it to be, if I choose it to be in the upper half plane, as I've drawn here, this is my 0 in the complex plane, this is my 1 in the complex plane, and they have some number z. If I choose it to be in the upper half plane, then it's unique. Okay. So that means that I have a map from the interior of the cardioid, or my general frozen curve. I have a map to the upper half plane, which is defined as canonical. If I take this triangle from my 0, 1, and z, and I take its 3 angles, these are 3 real numbers, that this is the direction of the normal to the shape in 3 space. Its normal has 3 coordinates, and the 3 coordinates are the 3 angles of this triangle. Okay. It's a little bit complicated, but it does reduce the solution to, it does give you sometimes a quadrature solution to this to the variational problem, because what it says, so if you come back here, so if you want to know what's the slope, I want to know what the function is here, what's the value of the function, what's the value of the different shape here. Well, your first step is, given your boundary, you find this, given the boundary of the domain, you find this algebraic curve from the condition that being rational, tangent, and so on, and inscribed. It's an algebraic equation. It's a complicated equation, but algebraic. You can solve it. Then again, to find the derivatives of this function at any point, you again solve algebraic equation, and then of course you can integrate it. So it's a somewhat elaborate procedure, but it does tell you a great deal about what the geometry of this solution is. And maybe I don't, I can't emphasize enough the importance of this, first the distinction between the physical plane in which randomness, in which somehow the physical plane which we observe, and this complex plane which has not so much to do with the, just the abstract complex plane. That is the plane which things happen. And that's an abstract complex plane. And I can't emphasize enough the importance of the map that goes from the interior of this of the disordered region to the upper half plane here. Because, for example, if you're interested in what the next step after the law of large numbers, the Gaussian correction, the central limit theory, then the conjecture is, unfortunately, it's still a conjecture, that the fluctuations here is just what's called free field here, the complex structure here, pulled back by this map. Maybe it's also instructive to see, well, it's instructive to see how this map degenerates as you go towards the boundary. Because if you go towards the boundary, then this complex tangent becomes real. It means this triangle, which was this number a over a plus b, becomes a real number. It means this triangle flattens out. And the three angles you get becomes 0, 0, and pi. Means the normal start pointing in one of the coordinate directions. You're going to get a facet there. And again, maybe to emphasize, sorry, to point this again, this in particular gives you if you take an ellipse or a circle, this does give you a complex structure on the interior of a circle. It's not the one you learn in complex analysis. It's something else. It degenerates as you go towards the boundary. So if you feel that this is a little bit too advanced, I want to say this: it's very easy. I mean, once you start working with things which are, that's what I said at the beginning. This sort of things, once you get algebraic geometry representations here involved, these things just start. But you can build extremely elaborate structures. In fact, there is a place in mathematical physics for all these structures, because one way in which this step surfaces appear in modern mathematical physics is not as observable surfaces, but rather as just parameter space in certain instanton sums in supersymmetric Gaussian string theories. And there, it's the that means you have you rewrite the original path integral as a sum over surfaces with certain weight, and the weight is a function of parameters, and it's only for certain very special values of parameter you get the weights we discussed, the uniform one. And however, this very strong integrability, it persists for all values of parameters. It's extremely complex, extremely sophisticated. And it's certainly great fun to study it mathematically. It does, of course. It's the minute you somehow start down this road, it does go away from most things. Here I could somehow point to crystals, point to other things, and this unfortunately does go away from all of that. It does go from the needs of our modern, current daily life. And I emphasize current is because with any cool mathematics, or interesting mathematics, let's not make pop culture of it. So with any interesting mathematics, you always hope there'll be some applications. And as our world gets, our daily life does change from the steam engines and we go to essentially we somehow we now live in extremely digital, extremely two-dimensional world, and it's one can hope that at least some of the mathematics we develop now will be eventually used. But as I said, unfortunately I can't. I'd rather skip this discussion now, and I want to go back to this to daily life questions. Of course, it's obvious from the how special the shapes we saw in the low flash numbers. It's obvious from how special the solution was that if I modified the setup just a tiny bit, all of that just has to go out of the window, just because the algebraic geometry is just too rigid to accommodate the you can't really modify algebraic geometry all that much. It's extremely. Yeah. So, and you can ask, what's the use of studying models that extremely special and allow for very elaborate solutions? Well, obviously, we do hope that in probability theory, that once you understood in great detail of a very particular model, the conclusions you draw from your analysis are, of course, the actual formulas are going to go out of the window. The qualitative conclusions about how the existence of these cusps and their number as a function of boundary conditions and so on and so forth, those will persist. So if I modify my model slightly so that the actual shape of the function of the entropy function modifies slightly, but the singularities remain the same or qualitatively the same, then I'm going to see a qualitatively similar picture. And so this very precisely solvable models, they are somehow one use for them is to help map out the various intricate behaviors that say random surfaces can exhibit. So that's and that's my. I think it's my last slide, and I'd like to stop here. Thank you for your